So now that we've talked about sequences, we're going to add one thing to our sequences and turn them into infinite series. An infinite series is a sum of an infinite set of numbers. And we're going to use our sequences to get this set of numbers. So the notation we used for a sequence was our curly braces, the name of the sequence A, and the subscript n to let our reader know that we were using n as the index. And this would generate just a list of terms that we separate with commas. So to turn this into a series, what we're going to do is we're going to use the Greek letter sigma on our sequence. And there's some values that we plug in here. Underneath the sigma symbol, we're going to state which value of n that we're going to start this series at. And above the sigma symbol, we write what value of n we're going to end it at. And in order for it to be an infinite series, we need to continue this sum forever. So the a sub n is just how we generate the list of numbers that we're going to add together. So if we start with n equals 1, we get a sub 1. So the difference now that makes this not a sequence is we're going to add to it the next term, which is a sub 2, and add the next term, which is a sub 3, add the next term. And we're going to do this forever. So your first thought when you see this is we're just going to get infinity every time, but that's actually not true. It all depends on what's happening within that sequence a sub n. If those values are going to 0, it's possible that when we add all of them together, that we will get a finite answer. And that finite answer is called the sum. So the limit of an infinite series is called the sum of the series. So remember back to Calculus 1. Most likely what you experienced in Calculus 1 is when your instructor presented a new concept, we typically teach you the technical definition way to perform whatever it is. And then later on there comes some shortcuts. If you think about derivatives, you most likely learn derivatives by first learning the limit definition with the difference quotient. But then later on we learn all of those shortcut rules with the power rule and the chain rule, the quotient rule, things like that. And this is not going to be any different. There is a technical definition that should work every single time for finding the sum of your series. But then after this section, all the rest of the sections in this chapter deal with the shortcuts for finding those sums. So before we actually learn how to do that, I just want to give you a quick example of what this is going to look like. We could be asked to find the sum from n equals 1 to infinity of 3n minus 2 over n squared plus 5. And what that means is we still generate a sequence of numbers just like we did before. The only difference now, instead of listing them out individually, we want to add them all together. So if we plug 1 in, I get 1 in the top and I get 6 in the bottom. Now instead of doing a comma, I say now I want to add to that the second term in my series, which I get when I plug in 2. So that's going to be 4 over 9. And then when we plug in 3, I'm going to get 7 over 14. And we could simplify that down to a half. And we're going to continue this forever and see, we're going to try to figure out a way to determine if those numbers will add up to something finite. So if the sum of a series is some finite number L, then we say that that series converges. Otherwise, it diverges. And diverges doesn't always mean that it goes off to infinity. It's possible that this sum like flip-flops back and forth between positive, negative, positive, negative, positive, negative, and never, as we go out many, many terms, never really narrows into one specific number that they're going to add up to. So, and that's called oscillating. So oscillating can also cause divergence. So the definition of the way that we do this, figure out that sum, is we create a sequence of partial sums. So we're going to look at what happens if we create a sequence of numbers where each term in that sequence includes one additional term from that sum in the series. Our partial sums, which is a sequence, is denoted as capital S sub n. It is a sequence, so we still write it the same way we write other sequence, but this is going to lead us eventually to the sum of our series. If it is convergent, the limit as n approaches infinity of our sequence of partial sums will equal the sum of our series. So our sequence of partial sums starts off with S sub 1. Just like every other sequence, we start by plugging in 1. And what that tells me is I'm going to add together the first 1 terms in the sequence. That means I'm just going to do the first term. S sub 2 means add together the first 2 terms of your sequence. So A sub 1 plus A sub 2. S sub 3, add together the first 3 terms. So you see the pattern here. Every time we generate a new term in our sequence of partial sums, we're just adding on what the next term in the sequence would be. So S sub 4 would be A sub 1 plus A sub 2 plus A sub 3 plus A sub 4. And if this sequence of partial sums has a limit, that's the same thing as saying, well, add together all your A's until you get to n equals infinity, which is exactly what that infinite series is asking us to do. So we're going to use a sequence of partial sums to find the sum from n equals 1 to infinity of 1/2 to the n power. Now, some of these partial sum problems are really, really tricky because once we generate this sequence, we won't be able to answer the limit part of the question right here unless I can take those individual terms and figure out the pattern for the partial sums. So let's try this one. This one should work pretty nicely. So our a sub n that we're working with here is 1/2 to the n. This is the sequence that is generating the terms for our infinite series. So s sub 1 means only use the first term. So if I plug 1 in, I get 1/2. S sub 2 means use the first two terms. So 1/2 plus, if you plug 2 in, you get 1/4. Well, 1/2 plus 1/4 is 3/4. And usually want to generate at least 4 or 5 of these in order to recognize a pattern. If we do the first 3 terms, we're going to have 1/2 plus 1/4 plus 1/8. We already know 1/2 plus 1/4 is 3/4, so now I just have to add 1/8 to that to get my next term, and I get 7/8. And then s sub 4, 1/2, 1/4, 1/8. And the fourth term on this sequence, 1/2 to the 4th power, would be 1/16. Remember, we already know the sum of the first 3, that's 7/8. So now we just need to add a 16th to that, and we get 15/16. So what we've figured out is our sequence of partial sums starts with these terms: 1/2, 3/4, 7/8, 15/16. And like we said in the last section with fractions, it's sometimes easier to recognize a pattern in the numerators and the denominators separately. And the denominators look like they're going to be pretty easy. I go 2 to 4 to 8 to 16. In order to do that, I've got to multiply by 2 every time. So anytime you see that common ratio, the value that we're multiplying by every time is the base for an exponential expression. Now, there isn't really a common difference or ratio between our numerator values. To get from 1 to 3, you've got 2 options. You can either add 2 or multiply by 3. To get from 3 to 7, you can either add 4 or just multiply by some obscure fraction. To go from 7 to 15, I'm adding 8. So there's not a common difference. There's not a common ratio. Another thing that we can check is, well, is there a pattern between these numbers? We were able to come up with an expression for our denominator, and if I can see a pattern between those numbers, I can write my numerator similar to the way I wrote my denominator. And for this one, it looks like our numerator is always 1 smaller than our denominator. So it's going to be 2 to the n minus 1. And if this series has a sum, it's going to be the same as the limit as n approaches infinity for 2n minus 1, 2 to the n power over 2 to the n. If you think about what happens as you plug very, very large numbers in for n, all you're going to get is a huge number in the top and a huge number in the bottom with just a difference of 1. You can, since technically that would be infinity over infinity, that is an indeterminate form, which means we could take the derivative of each and try again, and that's called L'Hopital's rule. Anytime you get infinity over infinity or 0 over 0, that means our numerator and denominator are growing at the same rate, and their derivatives will also grow at the same rate. The nice thing about the derivatives, though, is usually they're much simpler than the originals. So the derivative for 2 to the n, that's an exponential function that's not base e. So the derivative for exponential is always itself, and then times the natural log of your base. And then we've got subtract 1. The derivative for the subtract 1 is 0. And then in the bottom, we have that 2 to the n exponential again. The derivative of exponential is always itself times the natural log of the base. And all of this stuff simplifies down to just 1. That means our answer is 1. We're going to try another one really quick just to see if we can get this concept down, this concept of partial sums. So we are going to use a sequence of partial sums. To find the value of this infinite series, if it exists. So we might be able to get this to go a little bit quicker if we start by writing out what the terms for this sequence are. So if we plug in 1, we get 116 over 15. If we plug in 2, I get 236 over 30. If we plug in 3, we're going to get 356 over 45. If we plug in 4, I'm going to get 476 over 60, and we'll see if that's enough in order to do this. So for S sub 1, our first partial sum, you only use the first term, 116 over 15. For S sub 2, you add together the first 2 terms. And one thing I'm going to avoid when I do this is I'm not going to do any simplifying. It is possible for me to multiply that first fraction top and bottom by 2 and have a final answer here that has a denominator of 30. And the reason I'm doing that is so as I can preserve the potential pattern that we're going to see with these numbers. And when we do this, we get 468 divided by 30. So for S sub 3, I want the sum of the first 3 terms. We know the first 2 terms is 468 over 30. And now we're interested in including our third term, which is 356 over 45, which is 1058 over 45. I think we'll have a better chance of seeing a pattern here by forcing to keep a pattern in our denominator. So for the fourth term, just continue on the pattern. We already know the first 3 will make 1058 over 45, and now we're interested in seeing what happens if we include the fourth term, since we're doing our fourth partial sum, and our fourth term was 476 over 60. So when we take our previous sum, which had the first 3 terms, and then we add in our new term of 476 over 60, I get 283 over 9, but like I said, I was going to try to continue the pattern here. We had 15 times 2 is 30, 30 times, or 15 times 3 is 45, 15 times 4 should be 60, and if we try to get a whole number there, for 60 for the numerator, it actually does not work. We get a decimal. Which is 1,886.6 repeating. So it's definitely just not an obvious multiply by 2, 3, 4, and so on in the bottom. And because these numbers are getting so big, it's going to be really hard to recognize a pattern. What I'm going to do instead, when I write out the terms of my sequence of partial sums, I'm going to write them out as decimals. And I'm going to show you why I know this sequence or this sum is going to diverge. 116 divided by 15 is 7.73 repeating. And then 468 divided by 30 is 15.6. 1058 divided by 45 is 23.51 repeating. And then if we figure out the exact value of that last fraction, it's 31.4 repeating. So I'm not going to spend an hour or so trying to get the exact nth term for this sequence, but one thing I do see is that as I move from term to term, I'm having to add more and more every single time. So if I look at the difference between each of these terms, the difference between 15.6 and 7.73 repeating, it's about 7.8 or 7.7 repeating, somewhere around there. Let's say 7.87. For 15.6 to 23.51, we've got 7.91. And then 31.4 repeating minus 23.51 repeating, we've got 7.89. Now some of these might be slightly off because I didn't include the repeating part of the decimal, but it looks like every single time my sequence is increasing by about 7.9. So that tells me the pattern I'm going to see here is as I write more and more terms in my sequence of partial sums, I would expect them to get bigger every single time by about 7.9, which means this sequence is never going to settle down and stop at one particular value. It's just going off to infinity. So this sum diverges. So this last one is really tricky. And I'm not going to edit it out of the video because I want you to see it's not like Calc 1 where we could always figure out the derivative with our limit definition using that difference quotient. Some of these sequences of partial sums are really, really difficult to find the nth term. So if nothing else, I want you to see this just to kind of solidify in your head that this method is really difficult. So there is a lot of benefit that we're going to see from learning the shortcuts and all of the sections after this. Every different type of series is going to have a shortcut that we can use to determine if that series is convergent or divergent.